Yes. Okay, now we are on YouTube. So let me continue. As said here, in principle, we have to deform all structure. As you remember probably from the first lecture, the deformation of M0 is a some Poisson structure. In principle, deformation of delta zero is some additional structure, but in many examples, actually, we need not deform delta zero. So in many examples, we can take delta is equal to delta zero. Below I state some theorem which gives us this fact, but let's now assume that the situation is simple. Okay, then you see that I have prepared many formulas here. So assume that delta is equal to delta zero, and you see here we will do some computation slowly, I hope. But let's prepare for some notation. So for simplicity, I will not write for M0 for the product as the algebra A0, I just write a product AB. Product in the algebra A, I will write as a star product as I did before in the first lecture. So it will be just product AB plus H bar times first deformation, M1. And higher terms, and we have seen before that commutator, that M1 of AB minus M1 of BA, it is a Poisson bracket on the algebra A0, which we actually deform. And I also use some notation for the coproduct. Delta zero of A is A1 times A2, and maybe this first time I use such Swidler notations, so it doesn't mean that it is actually product, it's just a shortcut. So actually some summation is assumed here. Are there any question about notations?
The condition that we got Poisson bracket there is because of associativity, yes?
Yes. Yes.
Okay.
And the fact that initial algebra is commutative also is used.
And initial algebra is we assume
A0.
that, so we assume that we deform commutative algebra, yes?
We deform C of G.
Ah, okay, okay.
We are.
Sorry, how did the Poisson bracket appeared in A0? A0, we assume that it's a Hopf algebra on the previous slide.
But we showed in the first lecture that if we have deformation of the commutative algebra, that in the first term we have Poisson bracket.
Ah, that it satisfies the Jacobi identity, and yes.
This should be. I mean, this was shown or discussed at least on the first.
Okay.
So if you want to deform, then we need to have Poisson bracket. This is the main message, which I assume now we have. And now we look at this message in the context of the Lie groups. So so this is a general message, but since we now have a coproduct, all that stuff, this would impose additional condition on this Poisson structure, as we will see in a minute, or as you already see in the bottom of the slide. Okay. Now let us compute. So we can. I want to look at the condition that delta is a algebra homomorphism. This condition will lead us that these two terms, this and this, are equal. So technically, the delta of the product A and B is equal to delta of A times delta of B. Since I know something about the commutator, so here I impose commutator, and here I also wrote commutator. And so let me compute both the sides, green and blue. First, I want to compute green side. This a times b times minus b times a is equal to, okay, let me write with some color, is equal to what? Is equal to ab plus h bar m1 ab minus ba minus h bar m1 of ba plus O of h. And since our original algebra is commutative, we can, these two terms cancels. From these two terms, we get Poisson bracket. And since delta is h linear, we can move the h outside delta and get this formula. Okay. Now let's do, you see, longer computation. Delta of AB minus delta of A. Okay, so first I just substitute definition. So delta, oh no, sorry, I did a bit more. So instead of delta of A, I wrote A1 times A2, and instead of delta of B, I wrote B1 times B2, and so on. But this is not just a definition, because in principle, here I should have I have higher terms, but this higher terms will be H linear. And then if I compute commutator, and which I actually do here, it will give us again H because our multiplication is original multiplication was commutative. Give us again H linear terms. So all the difference here between delta and delta 0 is actually O H bar.
Сейчас, я вот не понял что-то. А ты считаешь примитивным элементом? Почему? Ну, элемент.
Where? I
Sorry.
didn't assume that A is primitive. A1, A2 are not A. There's some elements, I don't know.
So you assume a sum here, maybe.
Yes. Here the sum is assumed. Yes.
Okay.
For short. Okay. So this O of H comes because from the fact that the difference between delta and delta 0 have first order in H, and then since we compute commutator, we get second order in H. So we get H, at least H squared. So let's compute further. We
and here when you write A1 and A2, you assume that this is not deformed, or this is deformed coproduct.
A1 and A2 were defined for delta 0. So they are elements of the original algebra A0.
So probably I missed where is the first order deformation in the formula?
In this formula?
Yes.
It's here. Because we are not computing just delta, we're computing commutator. So we get first order, but then taking the commutator, since multiplication is
commutative. Multiplication is commutative.
And the zeroth order is commutative, so we get one order.
Okay, thank you.
Okay. Now for each of these products, I substitute this formula. So this is ordinary product plus H bar times M1. If I get everywhere ordinary product, so we get zeroth order in H, then I get 0. Since ordinary product is commutative, so all these terms will lead to the same. If I take everywhere here and here first order, I get second order, so it will be hidden here. So actually this sum will equal to the product, to the sum what's written here. So instead of each product, I substitute M1, one product, and another product. Instead of another product, I substitute M0 or just product. So I'm explaining this equality. Okay.
Сейчас это все умноженное на h-бар должно быть.
Yes, h bar is lost somewhere. Let me restore it again somewhere. Other questions or mistakes?
А откуда в первом равенстве появилась ома?
Here,
Угу.
because here we have delta, but in the definition we have delta 0. So this O is a difference between delta and delta 0 here.
А они разве не совпадают? В начале слайда написано, что мы предполагаем, что они равны.
Question. Maybe I do not need this assumption.
But A in the second line is not the same as A in the fourth line.
A in the second line. Where is the second? This line is second, or
I mean third.
this line? This A and this A are different, or maybe.
No, this A is from A0, and what we're computing there, A is from A.
No, this is from A0. Okay.
Blue
okay,
A is deformed. It also contains H series.
No. I mean, we have A is A0 power series in H. So we have A0 embedded into A. And we take elements of A0. This is a vector space.
So the blue computation is computation on the elements from A0, right?
So these elements A small and B small are from A0 embedded to A capital. And all these elements A1, B1 are all from A0. This is true.
Isn't the assumption is up to H bar? I mean, that delta equals to delta 0 up to H bar on A0.
Of course, but up to H bar is not assumption. This is just assumption.
Oh, yeah, this is.
Yes, I thought that I need. I mean, in the examples which we're going to talk about. Okay, so it looks like I do not need this assumption. So I will think more, but let me just write. Assume that I delete. It will be better because I will have more space on the slide. Now, Nikita, are you agree with this equality? So it becomes not trivial.
Yes, I agree.
Okay, so let's do computation further. You can complain that I again lost H bar. Let me restore it. But probably everything else is clear. We have a difference between M1 and M1. And since M0 is commutative, we get this formula. So combining green and blue computations together, we get this equality. And let me interpret this equality. It means that if we consider map delta from COG to COG times COG, this is the map of Poisson algebras. So here we have Poisson algebra because we have deformation, so it leads us to the fact that we have Poisson algebra, and Poisson structure here is defined. Of course, you can say defined by this formula. This is just in dual language. This is just a product of two Poisson varieties. So this formula should actually coincides with the formula for in the definition of the Poisson-Lie group. So as a result, we proved that if we want to have quantization of the C of G, then G should have Poisson structure such that the structure gives us a Poisson-Lie group structure on G. So G should be Poisson-Lie group. And this is why we can discuss Poisson-Lie groups, I don't know, like a month. So much time. Questions?
Maybe we forgot coproduct on the left-hand side of this equality.
Which equality? This equality?
Yeah.
Yes, maybe we forgot. So we definitely forgot. Maybe I couldn't be right. Other mistakes or comments? Koля, as I see, you have question always.
No, I just try to understand the relation with those which we discussed during last month. So we assume that A and B are functions on group, yes?
Yes, yes.
And this is exactly what was the property of Poisson-Lie group, that if you take a function of the product of elements, yes, we get like Leibniz-like rule on the functions, yes?
So if we take the function on the product, then the Poisson bracket, it will be the sum of the Poisson bracket with respect to first coordinate and Poisson bracket with respect to second coordinates.
And
Coordinates on the first factor and the second.
Yeah, I'm just trying to understand that I'm trying to convince myself that thing that's written on the right hand side is the same as taking Poisson bracket with respect to first or second variable, because it doesn't obviously look so.
Okay, let us write it somewhere.
I have to decompose into some series to understand this.
No.
Okay.
Okay, let us copy. We have, so what we compare this formula and formula which we have, I don't know, on the lecture 2, I hope. No. Everywhere. We're comparing these two formulas. So we change notation, so this A and B are phi and psi. But okay, I think it's clear that left sides are the same. So coproduct is just taken of function GH. Okay.
Yes.
And here we consider we first take our function. So we take in some sense you can think that we take our function psi of GH and wrote it as a psi1 of G tensor psi2 of GH. Assume that we can think that summation is here we have some summation, or you can believe that we are lucky and any function on the product is just a product of the functions. And the same for phi. or maybe it will be here without products, just because we're talking about functions. And now here we take the compute bracket of these two functions and then multiply, or compute bracket of these two functions then multiply. It's exactly as written here.
Mhm. Yeah, for me, probably it's simple to think about variation, not derivative, but variation. I mean, in a, like the form G at some something small, and then it's obvious that on the left hand side and on the right hand side we have the same. Okay, thank you.
Okay, if you convince yourself, then I'm satisfied. I try to say that these formulas are literally the same. You can find any way which you prefer. So this is the result of this slide. So if you want to quantize group, we need to have Poisson-Lie structure. Other questions? Okay. I want to support you by an example. I plan to talk about non-trivial example today, but we start from the trivial example. It is, my favorite example. We take group G with 0 Poisson bivector. Then, if we take 0 Poisson bivector, we do not need to deform our multiplication, so deformation remains the same. A slightly more non-trivial, or actually essentially non-trivial, is a case of dual group. I recall you that the dual Lie algebra is a G star with a 0 bracket. So therefore corresponding connected cell, simply connected Lie group is again G star as additive group. But here we have non-trivial Poisson structure, constant Kirill structure. Now we want to deform algebra function as G star, and this is algebra function of the on the dual space to Lie algebra is just a symmetric algebra on G. And actually, we know how to deform this algebra as an algebra. It is morally it will be universal enveloping of algebra. If we want to put H somewhere, then there are two ways to say it. Either we can take Riesz algebra, as I said, or we can think that our bracket is rescaled by H. Our structure constants will have factor with C times H. But morally, it will be just deformation of the universal of symmetric algebra to universal envelope. Unfortunately, in this example, we do not see anything about hope or something like this, because in this example, we have trivial Poisson bivector, and in this example, we have trivial coproduct. Not correct. A coproduct actually is not deformed, so coproduct remains co-commutative, so coproduct is not deformed.
And where is here non-commutativity? You say that we move.
This algebra is not commutative, but maybe it's not.
Why?
Universal enveloping is not commutative.
Yeah, I understand, but you have this is second example. Sorry.
We have two. We have, I don't know, one example or two examples. It depends how you count.
Okay. All is okay. Yeah.
No more questions about this example. Okay, of course they're trivial, but these examples are not hard. But anything we can check on, at least on them. Okay, we are in the middle of the talk, and we explained first two words in the title. The first two words were quantum groups. The next word was and algebras. So we are going to talk about quantum algebras. And quantum algebras are a deformation of not of the algebra of the function on group G, but a universal enveloping of the Lie algebra, U of G. U of G is also a Hopf algebra. We have a coproduct given by this formula. And it is easy to check that it satisfies the properties of the coproduct, and it's okay. And everybody who studied representation theory of Lie algebras actually knows that this is coproduct, because everybody who knows there is a tensor product of the representation knows that this is coproduct. So if it is not clear, then check. What and I will discuss next time, but what I'm going to say now and do not discuss next time, fact that this algebras are in some sense dual to algebra functions. So there is a pairing between algebra of universal development of Lie algebra and algebra functions. And the meaning of this pairing is the following. So we can, with universal development algebra, can be embedded into the algebra of the differential operators with this COG, namely, say, left invariant or right invariant differential operator. We can take any function, apply differential operator to it, and then take the value at the identity. Here I wrote it as a formula. So if we take any element of U of G, it is a linear combination of the products A1, say AN, where all these A's belong to the Lie algebra. Maybe I can write. So we take product of the exponents. So this is our, and then take derivatives. This is our way to write. So since here I used left invariant, left translations, it will lead to right invariant differential operator. And since I compute derivatives where in point where all t's are equal to 0, this is a value of z. The word dual means that this pairing interchange. So coproduct in one algebra and product in another algebra. So if we take a product of function of 1 and of 2 and want to compute this, instead we can take the coproduct of this operator, delta, and then compute pairing between delta of x, which is element of UG, G tensor UG, and these functions. It is clear from for the if in case of if x is a just element of the Lie algebra, then this identity means that if we take derivative to the product, it is a Leibniz rule. It will go to sum derivative to the first factor and derivative to the second factor, and this exactly corresponds to the fact that we have two summands in the coproduct, and it is also difficult to check this relation.
Does this pairing depends on PPV ordering? Because you take A ordered in some way on the left hand side, and on the right hand side you multiply corresponding group elements.
You need to check that everything is correct. Maybe this is what you're saying.
So it doesn't depend on
But
order.
this was that we take right invariant differential operators invariant definition. So here you have to check that. Here you have to check that everything is correct. So if you take say AB, take BA, take difference, then you get differential operator that correspond to commutator. And this from the fact that we have a map from Lie algebra G to the Lie algebra of the right invariant vector fields, and this is Lie algebra homomorphism.
Ah, okay, thank you.
But you're right, we have to check correct. For example, this duality leads the following, that our initial algebra, okay, what's my color? Let me write in black. Original algebra C of G is commutative as algebra function. Contrary to this, dual algebra U of G is co-commutative. So delta maps U of G to actually symmetric square of U of G, mapped to symmetric tensors. This is seen from the original definition. So it maps elements of the Lie algebra to the symmetric tensor. And then since any element is an algebraic combination of this element, then we, for any element, the coproduct on any element maps to symmetric tensor. So we somehow interchange our two structures. Okay. And as well as we discussed deformation of the algebra function group, we can discuss deformation of the dual object to the universal enveloping algebra. And this leads us to the notion of quantum universal enveloping, or I omit the word enveloping, quantum universal algebras, or better, say quantum algebras. Maybe just like quantum algebras. So,
and when you say dual, you mean that this pairing is non-degenerate, yeah?
It's a bit tricky. It depends on what kind of function to consider. But in some, so if you consider smooth functions, then it is not true. Then since everything depends in the neighborhood of the identity, this is not true. So what's true if, for example, if we consider completion of the function's identity, then it will be non-degenerate. Moreover, word non-degenerate somehow for infinite dimensional spaces. What does it mean? No, it means something. So I'm afraid to say wrong things about this question, so I ignore it. But morally, yes, it's morally non-degenerate, and there are costs of it.
And analog of universal enveloping for discrete group is group algebra, yes?
One can say that, yes. I don't want, but yes. Okay, quantum algebras. So our words are the same. So we have original algebra, U of G, A0, M0, and all such stuff. And we want to consider quantization. I should say that probably I just copied this three rows from the slide about deformation of the group algebra. Of course, there's a general notion of the deformation of the Hopf algebra, and here I just apply to two different situations. So definition is the same, but I want to give a couple of remarks here, and I already wrote them. First of them is the following. So if G is semi-simple, then there is no deformation of the U of G, not trivial deformation of U of G as an algebra. Actually, I gave a problem of the first lecture, problem we started, that corresponding Hochschild cohomology is equal to 0. So this, which proves that there is no trivial deformation. Maybe, so if you want to understand proof, then you use this, understand this problem. If not, you can use it as a fact in your mind that for examples which we are most interested in, your G is the same deformation will lead to the same algebra, but non-triviality comes in the comproduct. And the second comment is the following. So original U of G is co-commutative. If you consider deformation which remains co-commutative, then it will actually lead to deformation of the Lie algebra. And again, for semi-simple Lie algebras, there are no deformations. So we need to consider everything interesting comes in coproduct, and coproduct should be not co-commutative. Yeah, otherwise we get the same as we get. We don't have any actual quantization. Okay. Okay, so now assume that indeed our coproduct is not co-commutative. Then we can take difference delta minus delta opposite and divide by h. Since it is deformation of the coproduct of G which was co-commutative, so this delta minus delta opposite has 0 on the first order in h, so we can actually divide and then take mod h. So this delta of A is an element of the tensor square U of G times U of G. And let me state the theorem that this delta, G delta, is actually Lie by algebra. So you can should compare it with the previous example of the quantization of the algebra functions. Here we explained that the quantization of algebra function leads us to the structure of the Poisson-Lie group. Quantization of the dual objects should lead us to, I mean, if you contain one object, quantize, then we more or less equally quantize dual objects taken to the dual and ignoring the question about infinite dimensional vector spaces. So it leads us to the same structure, and since we work in terms of Lie algebra, this should lead us to Lie by algebra structure. As we explained, this is the same as Poisson-Lie group structure.
Sorry, and what is delta opposite?
But maybe you know, no? We just permute factors.
Permutation, okay. And h we write near delta, it means that it is okay.
I can write to 1 if it is maybe better. What? Subscript h or?
Yes, and
Subscript h stands for the coproduct in UH. I don't know. Maybe I should erase it. Maybe it's not important.
Okay.
Okay, let me erase it. Okay. Maybe I'm not going to spend much time in the proof, but I think I have like 5 minutes. So, and I'm not going to give a full proof anyway. You see the proof, and the end of the proof, you have problems that finish the proof. Such trick you should be familiar with. But I want to talk about the simplest, the first question which we have in this situation, because as defined, delta map from G to U of G tensor U of G. But in order to talk about Lie by algebra, we need to have map delta from to G tensor G, or even better, lambda 2 of G. So we have to show that actually we don't have difficult, I don't know. So this is infinite dimensional subspace, and this is if G is infinite dimensional, just infinite dimensional subspace. So this is strong restriction. Then it remains to prove cocycle and co-Jacobi identity for delta, and this is I left as a problem, and it's just some computation. Again, there's also everything's computation, but let me do it. So let's take delta of A, this deformation of the original coproduct, plus h bar times some product, some pi times ci. Here I wrote it explicitly. I mean, some explicitly. And let us use co-associativity property. So we have to compute delta tensor 1 times delta and 1 tensor delta applied to delta. So here the delta applied to the first factor, so either here or here. If we apply here, we can keep zeros in first order in H. If you apply here, we should keep just zeros order in H. Okay, apply here, then we get A tensor 1, 1 tensor A, plus, actually I use the same form, plus h bar times bi tensor ci. So if we apply delta to this term, we get this and this terms. Now, if you apply delta to the first factor, delta of 1 is 1 tensor R1, since delta is a algebra homomorphism. And so here we should have this factor. And let me correct the misprint. And if we apply delta to this, we keep only zero orders. This is delta bi times. Similarly, we compute this row. So we apply delta to the second factor here, these terms, and get the same classical part. Actually, I don't know why I wrote this classical part, because we know that the classical part should be the same both sides. And what is important for us is the first non-trivial term in H bar. Now we compare terms which have form bi times something tensor something. I wrote here explicit sum, so I assume that bi's are linearly independent. Something tensor something. And corresponding terms, what we have such term here, we have such term here. And in delta of bi, we have bi tensor 1 plus some terms low in degree. This delta is a, how to say, this regional delta for Lie algebra. Maybe I should write here delta 0. So the only terms which probably I should use here some sort of induction argument or like this, but okay, at least on the explain the idea, comparing the leading terms, we get here we get delta of ci, and here we have ci tensor 1 and 1 tensor ci. So we see that delta of ci is ci tensor 1 plus 1 tensor ci. So ci is a primitive element. And the only elements which we have in the universal field algebra, which satisfies this property, they belong to Lie algebra. Hence, delta maps to G tensor G, and since delta is obviously antisymmetric, delta maps from G to lambda 2 of G. It remains to show that delta satisfies cocycle and co-Jacobi identities, and this I left as a problem. Okay. Okay, assume it's okay. So we discussed already half of the title. So let me summarize what we discussed before. So we have the following statements. So first, we discussed deformation of the algebra function of G, and this leads us to Poisson-Lie group structure on G. And then we discussed dual objects, deformation, of universal value of G. And this is Lie by algebra. So this is why probably I should say this before. We spent like a month discussing all this such stuff. It's never too late. I hope so. And I didn't find better place as this slide to put the theorem, which I'm not going to use, but just say it if you want to have in mind. This is a theorem proven by Etingov Kazhdan. I'm a bit afraid how to write this Kashdan. That exists in some sense canonical quantization of any Lie by algebra. In principle, one can prove that any by algebra can be quantized. The proof used some technique, some different associator, and some. Instead of this theorem, we are going to consider examples, and we start from example SL2, and this will be all about examples for today, but let's discuss. Any questions before we start this example? So actually somehow a new theme for the lecture.
This quantization is not unique. Yes?
I'm not sure, bro. It is canonical, so maybe there is some group checks on such quantizations, but sometimes it's canonical. Word canonical, for example, means that if we have homomorphisms of Lie by algebras, then we have homomorphisms of the quantizations, so this equivalence of the categories. Other question? Okay. Now we are ready to discuss SL2. Probably we are always ready to discuss SL2. So here I wrote it's Lie algebra relations, and if I made a mistake, everybody can correct me. And here I wrote the coproduct, which we have seen last time. It is defined by classical R matrix, but you can just check it or anything. And before we proceed to quantization on the next couple of slides, I just want to comment that say that this Lie by algebra have two. I wrote hope it is not correct. Sub by algebras. Sub by algebras. What that means? B plus is generated by E and H, and it is a subalgebra, and our delta coproduct preserves it. Map B plus to B plus tensor B plus, and the same for B minus. So in order to quantize SL2, it is natural to first quantize B plus, then quantize B minus, and then somehow glue together these two quantizations. And this will be our strategy. We want to quantize B plus. I will use capital letters for the generators of the quantization. And as the algebra, I want to keep B plus the same. H and A just equal to 2A. And for coproducts, I want to keep coproduct on the H the same, because delta, which is a deformation of the coproduct for H, is 0. So it's natural to keep coproduct the same. But delta for E should be changed. But I wrote here not generic formula, but this formula because I want to preserve the gradient. Delta should be algebra homomorphism. We have a gradient induced by joint action of the H. E has gradient 2, so delta of E also should have gradient 2. So it should be a combination of the terms which have only one E. I wrote it here. So theoretically, I can write some factors also here, but I will not do it. Okay. You can ask what are f and g, and the answer is clear. They are a function to determine. Let's do it. Okay, maybe it is a bad point to slow down, but we do computation explicitly. So what we have to do? We have to compute delta tensor 1 applied to delta of E. What we will get? We get E tensor f of h tensor f of h plus g of h tensor E tensor h plus delta of g of h tensor E. Okay.
F of sum is sum of f's, or how you, or product of f's. When you take inner coproduct, where is the delta of f?
I applied delta tensor 1, so I applied delta to the first factor.
Ah, okay.
Maybe you complain about the usage of letter f. F is just some functions, not f generator of SL2.
No, I understand.
This I can correct, right?
I understand.
Fine. I don't know. Actually, I don't know
This
how to
is
correct
not necessary.
alpha, beta. No, I feel myself not comfortable with such problems, so I will do it.
And how you get these two copies of f in the first term, in the first summand?
Okay, now while I'm rewriting everything, using some indices and everything like this, I can answer the question. So I apply delta to the first factor of E.
Yes.
So instead of this E, I obtain E times G2 plus G1 times E.
Yes, this is clear.
So for example, I get E times G2 again times G2. So I apply delta to the first
Ah,
E.
okay, I see. Okay.
So actually, okay. Here delta applied to G1. Okay, now this
Can you repeat why do we have a second term in this sum?
This term.
Mm-hmm.
I apply delta to this E. Delta of E is this formula.
Ah, right.
Now one tensor delta applied to delta of E. So what do we get here? We get E times delta of G2 of H plus G1 of H times E times G2 of H plus G1 of H times G1 of H times E. Okay, we need to have equality. For example, we can compare terms with E on the first factor. Here we have E times G2 times G2. Here the first factor is not E, it's just under H. Here again some H. Here the same. So we came to the fact that delta, okay, hence delta of G1 of H is equal to G1 of H tensor G1 of H. And the same for the G2. Delta of G2 of H is equal to G2 of H tensor G2. Okay. This from terms where E is on the last side. This from terms where E on the first side. Terms where E on the middle. Happily cancels. Okay, I copy the slide.
Можно еще раз, а почему у нас эта разница должна выполняться? Почему у нас в одном порядке должно быть равно в другом? Это называется как?
Sorry. This is course associativity.
Хорошо.
Okay, so we get this relation. Okay, let me put as a problem the following facts: that if we have some g of h, h capital is group-like. Group-like means delta of g is equal to g tensor g. Then g of h is an exponent of some alpha h. Which is natural that if you want to element which is in which coproduct acts on the group element, then this should be a group element, and map from Lie algebra to group is an exponent. I don't have time. Okay, this is a problem, and applying this, we get that hence delta of E is E times some exponent of alpha 1 h plus some maybe alpha 2. Okay. Now, for example, using here we have actually we wrote two params, alpha 1, alpha 2, but if we replace E to E times in power alpha h, this leads us to replacement delta of E will be replaced by delta of E times E alpha h times alpha E alpha h. So using this, we can cancel one of these two factors. So without loss of generality, we can assume that we can send one of them. Let me look which of them. No, I don't have this written in my slide, so I have to look to the some notes, the textbook. We send alpha 1 equal to 0, and using the property which we want to impose, that delta of E minus delta opposite of E is equal to our delta small, is equal to E tensor h bar e tensor h minus h tensor e. This leads us to the alpha 2 equal to 1. So finally,
1 or h bar?
yes, h bar should be h bar. Actually, even here should be h bar, I think, because otherwise, what is the meaning of such exponent? Maybe I have to assume that g of h is equal to 1 plus h bar, 1 plus O of 1. Maybe that's not necessary, but okay, let me erase it. And we will see. So, okay, I put h bar here. So if I want, then I should put it everywhere. Everything become, okay, I will correct my notes, and alpha 2 is equal to 1. So finally we get, let me write with some other color. Finally we get delta of E is equal to E times okay. We have quantized the B plus, and everything was more or less straightforward. There's no essential another. Now we're going to quantize whole SL2, and probably here I plan to give some slow computation, but I will not. So I just state the answer. So we quantize B minus. So we have HF, and the only non-trivial formula will be formula for delta of F. And for delta of F, we pick F tensor 1 plus E in power minus H bar H tensor F. Again, here will be two exponents, and the only yes, I hope this is correct. Yes, as we can shift them by multiplication f by a certain exponent of h, and the only essential is the difference between these two numbers and these two exponents, which is fixed by the relation to delta, original by algebra structure, and we can pick like this. And if we combine all this together, so we get HEF with with delta given before, and the only relation we need to impose is a commutator between these two subalgebras, B plus and B minus. So we already defined coproduct on them, but we didn't define the bracket between E and F. And straightforward computation shows that this answer works and essentially more or less unique. I have planned to say something more, so I didn't spend my last 5 minutes in this computation. Maybe I left this as a problem.
Works for what? What do you have to check?
You have to check that under such definition, delta. You have to check two things. You have to get Hopf algebra, and this Hopf algebra is a deformation of the algebra structure which we had before.
Hopf algebra with multiplication, such associative multiplication that commutator satisfies this equation. Yes.
No, you can say that this is a free algebra generated by H, E, and F, quotient by these relations and the relation between H and E and H and F, which we had.
Okay.
Okay. I want to say two things, so I think it takes like 10 minutes. First thing is that I want to say, I said you before, maybe I should say it even here. I said you before that as an algebra, a universal development algebra of simple algebra, say SL2, do not have deformations, do not have non-trivial deformations. But here you can ask what's going on. Why do we have why we change the relation between E and F? If there is no non-trivial information, we can there should be a way to write something in terms of the original algebra. Of course, I can answer this just for simplicity, but then I have to show you how to relate this, how to show explicitly that this algebra is isomorphic to original algebra. And this I'm going to do in the next slide, again using problems. But let me explain what's going on. So in order to write formula for this isomorphism, and this isomorphism can be written as explicit formula, I will need a Casimir element. And this element C, which is written by any of these three formulas, is a central element of the original SL2. I recall that I used the small numbers E, F, and H for the generators of the original SL2, and I hope this is well known. And theorem, which we will prove in this problem, is the following: that there is a homomorphism of this universal enveloping of the H-deformed universal enveloping algebra to the algebra of series of SL2, and there will be isomorphism in this after the completion. So there will be an inverse map, and this homomorphism looks as follows: so E goes to E, H to H, everything simple, and F goes to again to F, but with some prefactor, and prefactor is some function of H and C. And also the function depends on H bar, which is our Planck, our deformation parameter. Okay, is the statement clear? Here I give some hint how to prove it. So what one actually have to prove the relation that commutator E and F, which is non-trivial in the universal envelopment of the SL2, on the quantum group, in the quantum algebra, goes to. So one should check this relation. So this goes to the same exponent where instead of H capital we get H capital, instead of E we get E small, and instead of F we get F small times some function. And this one have to check. So once do computation, do some formulas, and this lead to say difference relations this function which one can solve. So technically, the most important thing which simplifies computation is the following. So if you have E times any functions on H, it will be F of H minus 2 times E. So this is true for just function H, and this is multiplicative. So using this relation, this kind of relation simplifies computations for SL2, and at least this is my way to organize this computation. Okay. And as I said, there is an inverse map that can be written using the quantum Casimir. If you want, you can do this. You can consider it as another problem, but I don't think it's this. Okay, and last thing which I'm going to say is about quantum group, which depends not on H bar but on Q. And this last but not least, say. So take a breath and then let's discuss 5 more minutes. Are there any questions now?
Can you repeat, please, what was the role of Casimir elements on the previous slide?
Casimir element is used in this formula here. And to be, yes, used in this formula. Actually, it will look like that it appears in the denominator, but no, it's not. Okay, so when people talk about quantum group, quite usually they use letter Q, which is exponent of this H bar, and consider everything defined over the rational functions of Q, probably with some roots and something like this. Let me state what this. So Q is exponent of H bar. Exponent of the heating of this Cartan element will be denoted by K, and for it is quite always in that story we need some square roots. And I originally from the definition I defined that we don't have only K but also the square root of the K. Relations between K and E are K and F are the following. They again given follows from the same computation which we have here. So instead of F we now have exponent, and if we move this exponent through E, we get additional factor. I lost K here. Let me restore it. And relation between E and F is this, as this is just the way of rewrite. Concerning coproduct, maybe I ask the audience who can guess what will be the coproduct of K.
Who can guess or who know?
Who know? You know, if I understand correct.
K tensor K.
Yeah, and how to get this?
This is a group-like element.
Yes, this is exactly group-like element. So, like in this problem, exponent of the Lie algebra element, coproduct acts on them like this. And for coproduct of the E, we already have formula. So coproduct of the E is a E tensor K plus 1 tensor E. Coproduct of the F is a F tensor 1 plus K inverse tensor F. So this is another choice of parameterization, and actually another choice of the generators. So instead of generators E, F, and H, we have E, F, and K 1/2 and K minus 1/2. And there is one, it will be convenient for me to move to a bit different generators, A, B, and C. This is just rescaling, so by some number and some K. And after this rescaling, what do we get? So relation between A and B will look like AB is equal to BA plus Q squared minus 1 BA. Of course, I just so A is the same as K here. B I multiply by some which commutes with K. So it will be I should write just K squared times BA, but I prefer this way. And I will say you in a minute why. But before I want to write relation between E and F. Relation between E and now B and C. commutator of B and C is equal to what? So this K, so we have additional factors Q times Q inverse on the left of the commutator. We also have this case, but they cancel. So one of them in the product CB, they cancel because they stay here. And in the product BC, they will cancel because we will have conjugation of the element, which is H invariant. So here we'll get Q times Q inverse, K minus K inverse. So what I'm saying that this now if we consider Q is Q goes to one limit, H goes to 0, then all the commutators become 0. So you see, we actually get deformation of the commutative algebra. This is deformation of commutative product. I can write this if you want again as a commutator. Of course, I omitted the relation between A and C. Of course, this equally for Q goes to 1, it will go to 0. And what do we have for coproduct? Of course, delta of A is A times A. What do we have for delta of B? Delta of B will be what? Will be the I use this definition, so it will be Q minus half. Chi minus 1. It will be some. So what do we get? We get B tensor A plus A inverse tensor B. Okay. And so what I'm saying that we have deformation of the commutative product. So what is natural to think that we deform the algebra function some group, and it will be actually just dual Poisson-Lie group. Dual Poisson-Lie group is we said many times the product of two Borel subgroup quotient by H. So it will be a set of such pairs. The algebra function here is given by A and inverse B and C. And coproduct on this algebra follows from the product on this group. So you see, for example, from these multiplications, and coproduct of B will be A tensor B plus B tensor A inverse. So up to my mistake with A and inverse, we get this formula. And similarly for C. So UQ of G is a deformation of C of G star. So there are two ways to think about UQ of G. We either deform U of G, universal Felpin algebra, or we deform algebra on function, but on the dual Poisson-Lie group. Here I'm how to say, cheating a bit. So in order to say about formal deformation, first I impose Q, then I send Q to change. So actually, if one tries to say this correctly, then you need to have two different quantization parameters. One is responsible to one deformation, another to another deformation. But at least morally, I think everything's clear. We just change notation and see that we actually have deformation as a commutative. Okay, I am out of time, so let me stop here. These are the references. And if somebody has questions, I'm free to ask.
So when you say that we deform, can you please come back to previous slide? You say that UQ of G is deformation of C of G star, yes?
Yes.
And where is deformation parameter here? Or here is not non-deformed, yes?
Q as usual.
No, I understand. I mean on the right hand side. Here on this slide you got non-deformed product, yes?
Here we have non-deformed product, but C of G star is the algebra of commutative algebra of these functions, and the Q of G is the algebra of this A, B, inverse B and C with these relations. So these relations are deformation of the commutative.
Okay. So this is deformed matrix algebra here, yes?
What do you mean by matrix algebra?
No, C of G star. I mean.
C of G star is the algebra of functions. Oh, okay, it's commutative algebra. It's not matrix algebra. It is commutative algebra.
Algebra of functions in matrices. Yes.
On some matrices, this matrix.
And on the left side, you got product in this algebra, deformed product in this algebra. Yes. So the relations of the form product are here.
Yes.